All right, so new section for today, new topic. Really, ultimately what we're going to find is really kind of a continuation of ideas we've already talked about, believe it or not. It's going to look very different, though, at the beginning. You're going to start to notice patterns. Section 7.3 in the book. Now, the author lumps in Stokes' theorem and Gauss's theorem in the same section, which, I don't know, they're both pretty big topics. So this is another book section that's going to take us a long time to get through. Anyway, it is what it is. The book actually starts with a discussion of Stokes' theorem, and there's a natural motivation for that, but it's pretty non-standard, and I'm on the majority on this one. I think it makes more sense to talk about Gauss's theorem first, so that's what we're going to do here. So here we go. We're going to talk about Gauss's theorem. First thing you're going to notice, possibly as familiar as, hey, wait, haven't we done this already, is I'm going to start by talking about the ideas of boundary and accumulation and density. This is the same sequence of subheads, right, that we used when we were talking about Green's theorem. So, how about that? That's an eyebrow raiser. Why is this, I ask rhetorically? Well, you can probably guess. It's because structurally, Gauss's theorem that we're about to talk about is really a lot like Green's theorem in a lot of ways. And it's different, of course, thus the different name, right? But it's a lot of the same ideas. So anyway, something to kind of keep an eye on and something to be on the lookout for. Okay, now all that said, let's get into some details. I'm going to need to talk about the boundary surface of a solid region. We're going to be doing stuff on that surface. Namely, we're going to be talking about flux on that surface. Flux, if you think about it, is not defined on surfaces. Flux is defined on oriented surfaces. This was a big deal, right? It depends on which way your normal vector goes. Upward flux and downward flux are negatives of each other. We need to decide which one we're talking about. So, when I have a solid region R, that I'm going to shade in here like this, for example, and I want to talk about the boundary surface here. By the way, notice the boundary has kind of two pieces, if you will, because of the weird nature of this solid. If I want to talk about that boundary surface, if I want to talk about flux through that boundary surface, I need more than just a surface. I need an oriented surface. And so this word right here, boundary, needs to have a natural, default, assumed orientation. Now, again, I have to pause and point out, hey, this is exactly the scenario that we dealt with when we were talking about Green's theorem. Why were we looking at the boundary of a two-dimensional region? So that we could compute circulation, aka a line integral, vector line integral, which of course needs an oriented curve. Here, we need an oriented surface. Okay, so what is the convention? What does the word boundary mean? Boundary means as follows. The orientation for the word boundary, let me change my color coding. I don't like this color coding. Boundary means away from where the solid is. Okay, so for example, let's suppose we're at a point like this one on the surface, the boundary surface. If you were to go, this way, you're moving away from the solid. And I think that's a pretty easy pitch for that point. You're getting away, you're going away from it, right? But don't think globally, think locally. It's not because this is taking us far away from where we had been. That's not the point. The point is that at this location, in that spot, the other direction is there's solid right there. And then in the direction of the dark blue arrow, there's not solid. It's nothingness over there, right? So it happens to be, in the case of that particular point on the boundary surface, that away from the solid means outward. Okay. Just like with Green's theorem, though, this is a not generalizable thing. You cannot always say outward. It just isn't always outward. Look, for example, at this point right here. That's a point on the boundary. I mean, it's kind of the inside part of the boundary. Like this is a big, lopsided racquetball or something, right? It's got a lot of rubber. The R is where the rubber is, but there is a bunch of nothingness on the inside. So from that point, the solid, notice, near that point, the solid is over here on this side of that point. And so away from the solid means that way, which if anything, you would kind of need to call inward. Right? Does that make sense to everybody? So it's kind of like with Green's theorem, talking about boundaries on two-dimensional region. The temptation is to say counterclockwise. And, in a lot of cases, yes, but counterclockwise is, it's a little bit sloppy. What it is moving in such a way that the region's on your left. That was the actual convention. So likewise here, it's usually outward, but it's away from where the solid is. What do you think? Does everybody see the distinction? And is everybody okay with this as a convention? Reminder, conventions are arbitrary, and but it is a universal convention, and so it's not optional, but it was arbitrary 150 years ago, but now it's a convention. Okay, so let's talk about accumulation. We've talked a lot about accumulation in different kinds of quantities, in different kinds of contexts. So here, likewise, we have an accumulating quantity that doesn't look like it's an accumulating quantity. The quantity in question that we're going to be considering is boundary flux. Now, we actually did take a look at boundary flux back in chapter 6, and we were talking about Green's theorem and kind of the second version of Green's theorem, and flux through the curve as opposed to circulation along the curve and all that. And we have talked about boundary flux as an accumulating quantity, supplementally. But very importantly, now we're in 3 dimensions. We're talking about boundary flux defined on solid 3-dimensional regions with surface boundaries, not 2-dimensional regions with curve boundaries. So this is a new thing, but that's kind of the same idea in a lot of ways. So what do I mean when I say boundary flux accumulates? Well, if we look at this left side and ask, okay, for that left piece of the solid, what is boundary flux? Well, boundary flux is like this. Notice away from the solid, all of these arrows here, away from the solid are 1, for which we're talking about boundary flux. And then you look at this blue region over here and talk about, okay, what's the boundary flux on that region? Well, again, away from the solid. It's like that, right? Again, always away from the solid. When you see the word boundary, that means oriented away from where the solid is. So we get those pieces of flux. And, you can kind of see all this coming. If you were to look at the whole thing, on the whole thing, you'd have outward-oriented boundary flux would be like this. And you can see that most of the cancellation is going to, on this outside boundary, this green and this purple, cancel. This green and this purple, cancel. This blue and this purple, cancel. And this blue and this purple, cancel. And all we're left with then is this one shared face. That shared face, we're going to be computing flux on that shared face twice. Once as part of the boundary of the R1, once as part of the boundary of R2. Specifically, we're computing it twice with opposite orientations. They cancel. Poof, it goes away. And what we find is that, yes, the whole is the sum of the parts. When you're talking about boundary flux, chopping into pieces and adding it up works. This is an accumulating quantity. Let me pause there. Again, make sure that everyone's comfortable with that. All right. Okay, a quick reminder. Take a look at the picture from section 6.2 on the 2D divergence theorem. What you're going to find is that picture looks very reminiscent of this one. It's just two-dimensional instead of three-dimensional. Okay, so here's where I'm going to ask for your intuitive satisfaction. That I claim it doesn't matter how many pieces you chop it up into. Every time you make a chop, that's going to be part of the boundary of two sides. That'll therefore have opposite orientations. They're going to cancel. Chop all you like; it doesn't matter, right? And the next thing I'm going to ask you to be intuitively comfortable with is that means that you can think of our accumulating quantity in question as being made up of pieces that have location in the interior, which is weird because if I talk about the outward-oriented boundary flux on the whole, I compute it on the boundary. I think of it as being on the boundary. This is a red herring. This is cosmetics, right? I want us to think of boundary flux, outward-oriented boundary flux, as being actually distributed over the interior, right? And the way I'm going to try to make you comfortable with this is to change the name of it, right? So let's see, where did I write the word? Anyway, I'm just going to say flux here. Flux is a verbal cue. It makes you think about it being on the boundary. The clarification, boundary flux, emphasizes and reinforces this point of view of you thinking on the boundary. And again, this is all leading you in the wrong direction. So I'm going to replace the word, just for the purposes of this very brief discussion here, I'm going to replace the word boundary flux with made up sound blah blah. And now let me talk through the idea of blah blah, right, as an accumulating quantity. Okay, well, blah blah on the whole is equal to the blah blah on this side plus the blah blah on that side. Well, if you cut this solid in half, the blah blah, some of it's on the green side, some of it's on the blue side, but as a whole, the total blah blah is the same. Right now, that if I had said the word boundary flux, you would have been thinking boundaries. But if you think about the way I said it here, nothing about this feature of, hey, cut it in half, some's over there, some's over there, nothing about that says boundary. Right? This feature of accumulation intrinsically, this is how something behaves if it is in fact distributed on the interior. Right? So don't let the terminology take you in the wrong direction. And, yes, boundary flux, yes, it's computed on the boundary. It says boundary right there. But in terms of how you interpret it, in terms of how you think of it, in terms of how it actually behaves algebraically, this happens in the interior. Don't be fooled by the cosmetics. Does that make sense to everybody? You're willing to buy it? You can take that same blah blah concept and go back to section 6.2, I guess it would be, and reconsider circulation as an accumulating quantity and as being a kind of a stuff that's distributed over the interior. Okay. All right. So if it's a stuff, then we can talk about stuff per unit volume. Thus, we can talk about density. So, reminder, the term mass density means we're looking at mass per unit volume. Mass is an accumulating quantity. It has local locations. You can talk about where it is. You can talk about how much there is in a certain size. You can talk about how much of it there is per unit volume. Therefore, so again, density is accumulating quantity per unit size. So mass density, the accumulating quantity is mass, etc. So analogously, right? Talk about flux. Flux, we just agreed, is an accumulating quantity that you can think of as distributed over the interior. Don't let the linguistics kind of pull you in the wrong direction. And so likewise, if it has a location, color change. We can talk about how much of it there is per unit volume. And that is flux density. Now, I've used this term previously. I used it when we were talking about the second version of Green's theorem. And I made the observation then that, this term here, flux density, is actually extremely common, right? This is not me, trying to push a point of view. This is extremely common. In my physics classes as an undergrad, I heard the term flux density more than I heard the term divergence, which we're eventually going to rename this as. So heads up. I mean, that's a real thing. This is in your future. So flux density, not only terminology to be aware of, but it is a point of view that's extremely natural. It's extremely instructive and natural and useful. So heads up on that. But this is our idea of flux density. It's just stuff per unit size, and here's the formula for flux density, aka flux per unit volume. The formula is this right here. It's just how it turns out. Now we could go through and do computations, and I could computationally persuade you that the way that this is computed for a given vector field is by way of this formula. It's just details. It's just not what the focus of this class is. But it's not a particularly deep computation either. It's just sort of a matter of kind of writing things down and letting little boxes get smaller and smaller, and it's ultimately just a computation. So I'm not going to prove this formula. I'm just going to state this formula. And I think far more important than understanding where the formula comes from is understanding what it represents. So this formula, aka divergence, you'll recall. And furthermore, these notations. What do these things mean? They mean flux density. They mean accumulating quantity of flux per unit size. That's what this formula is for. Is that cool? Is everybody on board? Questions? Feel free. Everybody's all right? Okay. Alrighty. Well. So now before I put it all together, believe it or not, we actually have all the necessary tools at this point to pretty much write down Gauss's divergence theorem. Let's take a quick pause. Notice how familiar everything is. Notice how analogous everything is to Green's theorem. Now, different dimension. Yeah, it's three-dimensional instead of two. Sure, of course. It's talking about flux through the boundary instead of circulation along the boundary. Yeah. Totally different in that sense. Of course, different accumulating quantity, different dimensions, but structurally, it's all about orientations and accumulations and densities, just like Green's theorem. Okay, so again, before we put it all together, I want to flash back real quick to, back in chapter 6, we were talking about how you can think of the fundamental theorem of calculus as an accumulation, density kind of theorem, right? And I made this observation that as such, the derivative is change density, and that not only is this true, but it's also extremely familiar because, here's a ridiculous example, where between these 2 points, 1 versus 2, where is there more change happening? Well, yeah, if we just look at the derivative, see where the derivative's bigger. Well, the derivative is an indication of how much change is. Change doesn't happen at a point, it happens nearby a point, but you know what I mean, right? The derivative is telling you how much change is happening in the vicinity of a given point. And of course it's per unit size, that's all understood. And then we did these analogous computations here, making the observation that Green's operator, by virtue of being circulation density, tells you where the circulation is actually happening. I mean, by virtue of its values, it tells you where the circulation's coming from in the interior. And likewise, that divergence, this is two-dimensional divergence, of course, tells you where the flux is happening in the interior. where it's happening more and where it's happening less. So, well, here we are again. Now we have a new density, a new accumulating quantity density, right? Now three-dimensional flux density. And it's the exact same idea that if you've got some vector field and you want to ask, maybe it creates some total flux through some, outer boundary. Where is that flux really coming from? Between these 2 points here, which one of these 2 points creates more of that boundary flux? Well, you look at the flux density. Flux density, see where it's the greater. That's the point where more of the flux is being created. In the exact same way that the derivative tells us where more change is happening. You buy it? Everybody comfortable with that? So again, it's the divergence is very much playing a role of a density and an indicator of where the stuff is. The stuff being the accumulating quantity of flux in this case. Okay, whoa, I hit the wrong button there. Whoops, wrong button again. Here we go. Okay, so, all right, with all that in mind, here's Gauss's divergence theorem. Again, we're basically there already. We've already created all the pieces. We just need to put them together. Step one, we're going to view flux. Right? Flux. Notice flux computed on a boundary. Boundaries being understood to be outward oriented. Yeah. Flux is a quantity that you can think of as a kind of a stuff. It's an accumulating quantity. So the whole is the sum of the parts. It accumulates over the three-dimensional interior. That means that the whole flux, outward-oriented boundary flux, computed on that outward boundary, as a three-dimensional stuff accumulating over the interior, it is literally, I can chop up the whole into a bunch of little pieces and compute and add up the little outward-oriented boundary fluxes on all the little pieces. The whole is the sum of the parts. Yes?
This is like a best solving problem. So if the question asks is more flux, is there more flux that's like point A to point B?
Yep.
If one of them was negative, for example, it was negative 40 and negative 75.
Yeah, then you just have to pay attention to language. I mean, so it's like with change, right? Because let's go back to something that's extremely relatable. If you're interested, you could conceivably be interested in where is your altitude gain. Like if you're hiking on a trail in the mountains, the hiking trail is going to gain 500 feet of elevation. You might naturally be interested in where are you gaining the most altitude. But you also might be interested in where is there more steepness, right? Which positive or negative. So it depends on the I guess the phrasing of the question, the intent of the question, and that's the kind of thing that on an exam, if I were to ask something like this, you'd want to pay attention to the language. But if you aren't entirely sure what the intention of the question was, then just ask, and I'll definitely clarify during the exam. Yeah, does that make sense? Yeah. Very good question. Anybody else? All right. Okay, yeah. So, flux is a quantity. It's an accumulating quantity because the whole is the sum of the parts. All that interior cancellation business. Let's see. I'm going to have to. I'm not going to be able to quite squeeze this in. But the amount of flux happening on a small region can be related to density. Keep in mind, divergence is our flux density. So this equation I have in green could be sort of streamlined as flux equals flux per unit volume times volume. Okay. So flux equals flux per unit volume times volume. And how about that? Check it out. What we now have is a theorem called Gauss's divergence theorem. Among other things, which is this very unexpected relationship between boundary vector surface integrals and triple integrals. How about that? Isn't that wild? Yeah, there you go. So, what you use Gauss's divergence theorem for, well, there's lots of different applications, and you can use this as, we're going to do several applications. Let me not get ahead of myself. But most immediately and bluntly, what it can be used for, most obviously, is if you, for whatever reason, need to compute a boundary flux, which is a lot, by the way, if you're in engineering or physics, maybe even a little chemistry, physical chemistry side of chemistry. If you need to compute an outward-oriented boundary flux, and if you don't like that integral, hey, good news. There's a triple integral that you can compute instead. That might just be a lot easier. So even just sort of, bluntly, interpreted most immediately and literally. This is a pretty cool theorem. Is everybody with me? Let's do an example. All right, so let's see here. We have a surface given. The surface is the inward-oriented unit sphere. So that's this. There's our surface S. And on that surface, I am interested in this vector field F, also given. Specifically, I want to compute the flux. Vector surface integral, in other words, of that vector field through that oriented surface. Notice conspicuously missing from the statement of this question, conspicuously missing is the word boundary. It doesn't say the word boundary anywhere. This question does not immediately present itself as use the Gauss's divergence theorem because, all the keywords are there, right? This just says compute this vector surface integral. And so we've got to decide now, is this a computation that is appropriate for using Gauss's divergence theorem? Okay, and frankly, the most immediate answer to the question is no. It's not. Because we are computing an integral. Here's my surface S, right? Got a picture of our surface S. That's my domain, and it's not a boundary. And a very, very important, and now I know you've heard me say this a million times. I'm going to say it a million more. Every one of these accumulation theorems has a catch. And the catch on Gauss's divergence theorem is that your domain for your flux integral has to be a boundary. It says so right there. It could not be more clear, right, in the statement of the question. But it's a very important disclaimer slash requirement of the theorem. It only addresses boundary fluxes, and we are not looking at a boundary as it stands. Everybody see the problem? Okay. All right. Fair. It is not a boundary. Bummer. Now, a little bit of side work. I'm going to point out that if I were to look at the same underlying surface but orient it that way, that green surface is a boundary. Oh man, I sure wish they had asked me to compute flux through that green surface, because I totally know how to compute the flux through that green surface. It's a boundary. I'll use Gauss's divergence theorem, and yay. But they didn't. They asked me about the blue surface. So the good news, of course, you can predict this based on our first example of using Green's theorem. Same story arose. I just have to recognize these two surfaces are opposites of each other. Same underlying surface, opposite orientations. And so the relationship between the one flux and the other flux is a minus sign. Orientation means a minus sign in the evaluation. Is that cool? So what I've done then is I've connected the non-boundary question that we were explicitly asked to a boundary question, which is easy, for which we have tools anyway, I'll say. Okay. All right, so with that part done, now let's think about our surface here, S minus, which we again just agreed that's a boundary. What is it a boundary of? Well, it's the boundary of this ball. Right there, right? B is the unit ball. That's that's what my green S minus is a boundary of. And so let's recognize that S minus, S minus is the boundary of the ball. And with that recognized, I can now say, oh, goody. Now I am literally looking at one of the sides of the Gauss's divergence theorem. Flux through the boundary of a vector field. That is straight up exactly what I've got there. And so I'm going to cite Gauss's divergence theorem and say, you know what? I'm going to rewrite that boundary flux as a triple integral of divergence. There we go. Everybody good? Don't lose your minus signs. It's really easy to accidentally, this minus sign that we very importantly had to include for, important conceptual reasons, that keeps on, right? Don't, you don't just kind of put it in there as a doff of the cap and then throw it away, right? It's got to follow along as well. Okay. All right. So, now we have a new question before us, right? The original question was to compute a flux. Oh man, parameterize a surface. Oh gosh, it's a sphere. Oh, the trig is, here comes the trig. It looks like a scare. Oh my gosh, and look what I'll be doing to the trig. I'll have e to the power of trig. This is looking ugly, right? So the original question was brutal. Now, I have a triple integral question that I've turned it into. Triple integral of the divergence. Divergence is easy to compute, as it turns out in this case. This divergence here, it's just 3 plus x. Now, that's a little bit of partial derivatives, right? Let's think that through. I need to keep in mind, make sure you know the formula for divergence. Very important to have that, like, boom, right there on the top of your head. I need to take the x partial of that. That gives me the 3. The z cubed goes away, disappears in a puff of smoke. Gotta love it. The y partial of this is just x. All of this other ugly here doesn't have any y's in it, so it disappears in the partial. Again, puff of smoke. Bye-bye. Thank God it's gone, right? That was a scary expression. And then we need the z partial of that. That's 0. There are no z's in there, so poof, that's gone too. So the question has simplified dramatically to just computing this one triple integral. Now, to be fair, I recognize that this is still a round thing, right? I'm still concerned about the possibility trig's going to show up, or square roots, which I consider to be worse, right? But we have a different option on the table. We have a different thing for which we have different tools. We have a hope that something's going to work out really nicely. And in this case, the way it works out, I think this is a lovely trick, by the way, is to, let's begin with the colors. Separate it into 2 separate integrals. And even though this integrand here doesn't have any particularly nice features, each of the pieces of it does. So 3 is awesome. It's a constant. I love constants. Right? X, oh, that's got the potential for a symmetry argument because it's got odd symmetry in a certain direction. So I love that too. This is a weird thing to be on the lookout for. Surprisingly common to have an integrand which by itself has nothing good to say about it, but the individual terms do. So always be open-minded to the possibility you might break up an integral into a sum of 2 integrals and everything might just kind of fall apart. So I'm going to let y'all read the details I'm going to let y'all produce for yourselves the details as to why this integral is 0. Again, think through the details, right? It's very, very specific. That integral is 0. Integral of a constant is just constant times the volume. And game over, we win. Didn't have to do any trig at all. Everybody happy? Okay. Cool. Obviously, this was a manufactured example, right? But it remains the divergence theorem is extremely useful for computing boundary fluxes in a lot of cases. Okay, so now I want to talk about some physical examples. The three-dimensional divergence, Gauss's divergence theorem, it's very naturally models a lot of physical scenarios. It's one of the biggest theorems used in, electricity and magnetism. It comes up significantly if you're trying to understand gravitational forces, gravitational fields. It's a big deal in a lot of fluid flows make a massive use of Gauss's divergence theorem. It's a really big deal in the three-dimensional world. By the way, I asked the engineering school one time, and I bring up engineering a lot because I know a lot of y'all are engineers, right? Just appealing to my audience here. I asked the engineering school, what do y'all think? For your purposes, what's the most important part of a course in multivariable calculus? And they gave me the sort of the real estate location answer. The first most important thing is the vector calculus theorems of Gauss and Stokes. Second most important thing is the vector calculus theorems of Gauss and Stokes. The third most important, y'all know the old joke about location for real estate? They gave me the same answer for this. So these physical interpretations of the divergence theorem are a really big deal. Okay, so let's talk about one. I claim that a light bulb is a wonderful example of Gauss's divergence theorem in play. So, what do light bulbs do? Light bulbs, and by the way, let me make my light bulb over here. There it is. There's my little light bulb hotspot. That's where the filament is, or the LED, or whatever. Right? What does it do? It generates photons. Right? Makes light. That's the name. And I'm sure y'all all know, but just to repeat, just in case, light comes in the form of tiny little particles called photons. And the flow, of course they flow, right? Photons don't sit still. Photons are flowing. That flow is what light is actually made up of. So it's literally the flow of a fluid. That's what light is. It's the flow of a fluid. Is everybody okay? All right. Okay, so again, these photons flying out of the light bulb, like so. All right. Now let's talk about the picture a little bit, though. Yeah, sure, they're flying out at the light bulb, but they always go the same speed. Famous fact of relativity. So why are these arrows smaller? The further you go out, I have my arrows getting shorter. Are the photons slowing down? No. Keep in mind, one of our primary ways to represent fluid flows is not just with velocity, but velocity times density. And the further you get away, the lower the kind of the density of the photons is. There's, that light bulb over there there's a lot of photons per unit volume near the light bulb, but way over here where I am, they've spread out quite a bit. There's just not as much density. So that's why these arrows are shorter. Does that make sense to everybody? Okay. All right. That said, photon density does not change over time. We'd be in trouble if it did, right? If photons were just kind of accumulating and getting more and more and more, that eventually there'd be some sort of photon bomb explosion that would happen. It's just not the way it works. As long as we're in what we call a steady state situation, the light bulbs are emitting a fixed amount of photons. As long as nobody moves, right, then the photon density is constant coming out of a light bulb. Does that make sense? All right, so let's think about what divergence means then. What is divergence? And previously, I made the observation that divergence tells you where the flux is coming from, right? And now let's play that out in this scenario. Let's think about this surface here. That surface is going to have a certain amount of photon flux this photon fluid flows through that surface a certain amount. Where'd that flux come from? Did it come from, is light being emitted out of the sphere itself? No, the sphere is just, this is just an arbitrary surface that I drew just to ask a question. That's not where the photons are coming from. The photons are coming from the light filament, or the LED. And if you were to compute the divergence of this flow field, what you would find is that the divergence near the origin, where the actual LED is, and LEDs are small, but they're not points. They do have some size, just a tiny, very small amount. On that very tiny little bit of volume that the LEDs make up, the divergence would be massive. Everywhere else, you know what? I color coded this poorly. Let me do this. Get back in orange. Okay, so where the hot spot is, the divergence is going to be huge. Everywhere else, like along in here, let's say at this blue point right there, are there any photons coming from that spot? And now there's a temptation to say, well, there's a lot of photons in that spot. And the retort is, well, yeah, but they're not coming from that spot. Any photons that emanate out of that spot previously entered in to that spot. Nothing's being created, photon-wise, in that spot. That's not actually a source of anything. And that, algebraically, is represented by divergence being 0. And again, if you were to write down the vector field for this scenario, compute its divergence, the divergence would literally be 0 at that blue spot. All right? Everybody okay with that? So, as previously claimed, divergence is the giveaway. Divergence tells you where the photons are actually coming from. Measured in the form of boundary flux, fine, but where did that boundary flux actually come from? It came from where the divergence says it came from. It came from, in this case, the little hotspot LED at the, in a very small amount of volume at the center. Everybody's good. Okay, now, next example. So here, this is a weirder scenario, I suppose. I'm imagining that we have a large balloon, and there's a certain amount of gas inside of the balloon, and then I'm imagining that the balloon is going to expand. Now, why is the balloon expanding? Maybe the temperature is rising, and as a result of the temperature rising, the thing expands, or whatever. Right, what the physical scenario is, let's not worry too much. But you can imagine that if that balloon starts to get bigger and bigger, well, the gas that's on the inside has to kind of go along with it, right? And so as this gets bigger, little particles of gas follow. And notice that it's radially outward. Furthermore, notice that the velocity of that gas depends on where you are. And so, for example, if you're at the center, that little piece of gas at the center, well, it's kind of in some sense being pulled by all sides, and it ends up not moving at all. And little pieces of gas that are close to the center, well, I mean, they move a little bit, but not really very much, because they're being pulled from the other side as well. So I propose, and I think this is a reasonable claim, that this vector field is it's proportional to the position vector. It's always radially outward, and the further you are away from the origin, the faster you have to kind of follow along with the edge of the balloon that you're near. So I hope that seems kind of plausible. Is that all right? Okay. All right. So this is a different vector field, different physical scenario, and I want to point out some pretty significant distinctions between this physical scenario where I have a gas kind of flowing outward versus this physical scenario where I have photons flowing outward. The big distinction, the photons are being generated we're literally making more photons all the time, right? But the density is constant. So they're being created and they're just kind of passing through wherever they go past. So the photons are being created. Let's say the fluid is being created, but the density is constant. And it's the opposite here. Here, the density is not constant. As the gas expands, the density is decreasing. The density is the thing that's changing. Whereas nothing's being created. So, I mean, that's a little weird, right? But this is a fundamentally different kind of a fluid flow situation in terms of the physical interpretations of what's actually happening here. This fluid flow is all about representing density changes with nothing being created. This vector field is all about stuff being created with no density changes. So you got to keep that in mind. This is an ugly little reality when you're trying to make sense out of vector fields and fluids and fluxes and what does this mean in the real world. You better make sure you know what kind of a fluid you're dealing with. Is this a fixed amount of fluid that's moving and changing density, or is it a fixed density that's being created? Okay, so anyway, enough of that. Okay, so let's take a look at what the divergence theorem says. Here's the divergence theorem applied to this picture, right? Specifically applied on this fixed sphere right there, and I emphasize that blue sphere. That's not the balloon. The balloon is outward of that and moving. This is an interior blue sphere that is a fixed size. It's not changing at all. Okay, so we write down the divergence theorem. It's pretty easy to compute the divergence of that vector field. Make sure you can do that, by the way. Again, you got to think through the formula, think through what the coordinates are given the formula for the vector field. Make sure you're good with that. But the divergence, though, is constant. So what does that mean? Here's what I say it means. The flux here, flux is computed on that boundary. The flux is measuring how much, as our exterior or outer balloon is expanding, there's a lot of gas that is literally leaving through the boundary of this blue boundary sphere of our little interior there. Gas is leaving. Gas is disappearing out of there, right? And the divergence, is telling you where it's leaving from. Now, again, let's not get caught up in semantics. Where is all the gas leaving from? Well, it's leaving at the border. It's leaving at that's when it was inside, then it crosses through, and now it's not inside. In some sense, it's leaving at the boundary. Well, okay, but of course it is. But where really did it come from, right? And where it came from is uniformly distributed over the interior. Because this gas leaving through the boundary is that's really kind of a symptom of the more underlying reality, which is that the density on the inside is decreasing. The gas that's on the inside, there's getting to be less and less gas everywhere, uniformly throughout this interior. And the fact that this is a constant points to how this is uniformly through the interior, and the decreasing density in that interior. That's why we're getting flux on the boundary. It's because the gas on the inside is departing. Does that make sense? So, again, different physical interpretation because it's a different physical scenario. But same theorem applying in these two very different scenarios. Real quick comment, and then we'll call it a week. The two examples that I showed were kind of extremes. In one case, with the photons, we were generating fluid and no density was changing. In the second case, we had changing density and nothing was being generated, right? So we had very different kinds of fluids. In some cases, both are happening. Fluid is being generated, and furthermore, the density is changing too. Right, and when that happens, this is the kind of the global relationship between the objects in play. The way I like to think about this is that if fluid is being generated, there's really only two things that can happen. If you're making fluid, then either the fluid that you're making leaves, in which case it counts as flux, or it doesn't leave, in which case it contributes to the rising total quantity of fluid on the inside. And if you just divide by dV across the board, flux turns into flux density, mass turns into mass density, and this I call this generation rate density. How bright is your light bulb in that particular place? And so what you have then is a relationship that allows you to interpret divergence in relation to these two possible aspects of the fluid flow. Okay, drawing the line right here. Y'all have a good weekend. See you on Monday. Don't forget to make sure that I mark you down for attendance.